When 3I Atlas made its closest pass by Earth, nothing dramatic happened in the sky. No flash, no visible spectacle, no moment most people would ever notice. And that silence is exactly why this moment matters. Because while the object is already moving away at tens of kilometers per second, heading irreversibly back into interstellar space, the data it left behind has only just begun to speak. And what that data is telling us does not sit comfortably with what we expected to see. This wasn't a dangerous encounter. There was never any risk of collision. The object passed at a safe distance of roughly 270 million kilometers. But something about its behavior before, during, and after that passage has changed, and we are already detecting the consequences. The object is gone, but whatever happened did not end when it left Earth behind. The trajectory of 3I Atlas tells us one crucial thing. This object is not coming back. Its orbit is hyperbolic, meaning it is not gravitationally bound to the Sun and will never return to the inner solar system. Once it reaches the outer regions, it will disappear forever into interstellar space. In most cases, that would also mark the beginning of a slow and predictable decline in activity. As distance from the Sun increases, thermal energy drops, sublimation weakens, and cometary behavior gradually fades. That is the standard model, the curve astronomers expect to see every time. But 3I Atlas is not following that curve. Instead of a smooth decrease in brightness, telescopes are recording sudden increases followed by sharp drops, repeating again and again. This is not random noise. These fluctuations are coherent, persistent, and most importantly, synchronized across independent observatories in different parts of the world. Chile sees it. Hawaii sees it. Space-based platforms see it. When different instruments agree, the signal is real. Researchers have started using an unusual word to describe what they are seeing: a pulse. Not as a metaphor, but as a measurable rhythmic fluctuation in brightness and activity that appears shortly after the Earth flyby and continues as the object recedes. In normal cometary physics, activity decreases after perihelion. The system cools, energy input drops, and the behavior stabilizes. Here, the opposite is happening. The object brightens abruptly, dims, then brightens again in a repeating cycle. The first instinct is to attribute this to rotation, a spinning body with an active region briefly facing the observer. But the timing, regularity, and stability of these pulses do not match simple rotation. The data suggests something more complex, a combination of rotation, wobble, and internal imbalance. This implies internal structure, not a uniform block of ice and rock, but something layered, fractured, or unevenly distributed in mass. Here is where the puzzle deepens. Despite signs of rotational complexity, the jets associated with this activity remain remarkably precise. They do not fan out chaotically. They do not disperse randomly. They are narrow, directional, and repeatable. This is an unusual combination. In natural systems, rotational instability tends to produce messy outflows. Precision usually comes from confinement. That confinement could be caused by highly structured emission points or by channels that guide material outward in a controlled way. In known natural objects, strong confinement typically requires significant magnetic fields or deep gravitational wells. A small interstellar body should possess neither at meaningful levels. This does not imply anything artificial, but it does place pressure on existing natural models. We are seeing instability and control at the same time, a pairing that is not common in cometary physics. The timing of this behavioral shift is not arbitrary. The onset of the pulse coincides closely with the moment 3I Atlas exited the region where Earth's gravity has its strongest relative influence. This raises a subtle but important possibility. Earth did not cause the activity, but it may have triggered it. Even weak tidal forces can generate stress in bodies that are fractured, layered, or structurally complex. If the object contains trapped volatile pockets beneath a crust, those stresses could produce episodic releases rather than continuous outgassing. In this scenario, what we are observing is not a new phenomenon, but the latest iteration of a process that may have been activated many times before, near Mars, near Jupiter, or even around other stars millions of years ago. Earth did not change the object's nature. It may simply have nudged an already sensitive system into a new phase. Once the pulse was confirmed as real, attention shifted inward because rhythmic behavior almost always points to internal structure. A simple, homogeneous body does not pulse like this. If 3I Atlas were a solid, uniform mix of ice and rock, its brightness variations would track rotation cleanly and predictably. Instead, the data suggests a system that is dynamically complex, potentially layered or fractured, with uneven mass distribution. That kind of internal architecture allows stresses to build, release, and rebuild in cycles, producing episodic activity rather than a steady decline. The important detail is that this behavior emerged after the Earth flyby, not before, implying the system crossed a threshold. Once triggered, the object didn't settle back into equilibrium. It entered a new regime of behavior that persists as it moves away, which is not what standard post-encounter cooling models predict. At the same time, the outflows associated with these pulses remain sharply confined. Gas and dust are not spreading into a broad fan, they are being expelled along narrow, repeatable paths. In natural cometary systems, this level of collimation usually breaks down as activity weakens and structural coherence degrades. Here, the opposite is happening. As the object recedes and overall energy input drops, directional precision remains. This suggests that the emission points are not random surface fractures but stable, well-defined channels. Whether those channels are formed by internal layering, compositional boundaries, or long-lived cavities, they imply a degree of organization that is difficult to reconcile with a loosely bound rubble pile. The system appears dynamically unstable on a global level, yet locally constrained where material escapes. Spectroscopic data adds another layer to this picture. The observed ratios of carbon dioxide and methanol relative to water vapor are unusually high, pointing toward formation in an environment far colder than the Kuiper Belt. In such conditions, volatile compounds that would normally be lost early can remain frozen and preserved for billions of years. This alone makes 3I Atlas scientifically valuable, a direct sample of chemistry from another stellar system. But then nickel enters the story. Emission lines of nickel appear clearly in the coma, while iron, which almost always accompanies nickel, is weak or absent. Separating these two elements at this scale requires unusual chemical pathways. One proposed mechanism involves nickel carbonyl, a volatile compound that can vaporize at relatively low temperatures in carbon monoxide-rich environments. The chemistry is plausible, but it has never been observed operating so cleanly in a natural object, and it still doesn't explain why the resulting outflow remains so narrowly focused. Then there is the anti-tail. In standard comet physics, material is pushed away from the sun by radiation pressure and solar wind. Apparent sunward tails can sometimes be explained by viewing geometry, but here geometry alone does not resolve the observations. The data suggests a physical flow of material moving at least partially toward the sun, resisting forces that should disperse it. Even more striking, that flow is persistent and collimated. Gas expands. Dust spreads. Narrow streams require shaping. This does not imply an artificial origin, but it does demand a shaping mechanism we do not yet fully understand. It is at this point that many existing models begin to strain, not because they are wrong, but because they were never designed to handle an object with this combination of chemistry, structure, and dynamical behavior. What's becoming increasingly clear is that whatever changed during the Earth passage did not simply fade away once the object moved on. The pulsing behavior continues as 3I Atlas recedes, which implies the system has shifted into a new operational state rather than experiencing a brief disturbance. In physical terms, this suggests a threshold was crossed. Once internal stresses were released or internal pathways were opened, the object did not reseal or stabilize. Instead, it settled into a repeating cycle, like a mechanical system that has slipped into resonance. Natural bodies can do this, but it usually requires a very specific internal configuration, one that stores energy and releases it periodically. The persistence of the signal tells us this is not a transient flare, but an ongoing process. Earth's gravitational influence is weak compared to the Sun's, but weak does not mean irrelevant. For a body that is fractured, layered, or internally complex, even small tidal gradients can act as a catalyst. The timing strongly suggests that the object's exit from Earth's zone of strongest relative influence coincides with the onset of the pulsing behavior. This doesn't mean Earth caused the activity in a direct sense, but it may have acted like the final tap on an already stressed structure. In this context, Earth becomes part of a longer chain of interactions, one that may have included close passes by other planets or stars long before this object ever entered our solar system. What we are observing now could be the cumulative result of repeated tidal interactions over millions of years. As more data is analyzed, it becomes harder to fit 3I Atlas into existing cometary models without extensive modification. Standard models assume relatively simple internal structures, gradual thermal responses, and predictable post-perihelion behavior. Here, we see abrupt changes, rhythmic activity, precise outflows, and chemical signatures that diverge sharply from expectations. Each anomaly can be explained in isolation with enough assumptions, but when combined, those assumptions begin to pile up. This is often a sign that the model itself is incomplete. Not wrong, but built for a narrower class of objects. Interstellar bodies, formed in environments we've never directly sampled, may simply fall outside the comfort zone of those frameworks. Beyond the specifics of this object, 3I Atlas is forcing a larger realization. Interstellar objects are not just fast-moving curiosities that briefly pass through and leave. They can be chemically rich, dynamically active, and structurally complex, even after leaving the region of strongest solar influence. The fact that this object was discovered relatively late in its approach highlights how easily such visitors can slip past our detection systems. If 3I Atlas had been slightly smaller, darker, or faster, none of this data would exist. The implications extend beyond this single case, suggesting that the galaxy is not a quiet backdrop, but an active environment through which material regularly moves, interacts, and occasionally surprises us. One detail that keeps resurfacing in the data is coherence. The pulse is not drifting, not decaying, not desynchronizing as the object moves farther from Earth and the Sun. Instead, it remains remarkably stable in both timing and amplitude. In astrophysical systems, coherence over time is difficult to maintain without an underlying structure enforcing it. Random outgassing produces noise. Thermal relaxation produces smooth curves. What we are seeing instead is a repeating pattern that survives changing external conditions. That tells us the driver of this behavior is internal, not environmental. The object is not reacting passively to its surroundings anymore. It is operating according to its own internal dynamics, and that alone makes it an outlier among known cometary bodies. The pulse has also allowed researchers to infer aspects of the object's rotation that were previously inaccessible. The data does not support a simple spin around a single stable axis. Instead, it points toward a combination of rotation and wobble, a complex motion that implies uneven mass distribution. This is exactly what you would expect if the interior were layered, fractured, or contained cavities of differing density. Such internal heterogeneity would explain why stresses accumulate and release episodically rather than continuously. Importantly, this kind of structure would also allow channels to remain stable even as the bulk motion of the object becomes irregular, resolving the apparent contradiction between global instability and local precision in the jets. Another implication of the current behavior is memory. Physical memory, not conscious, but structural. The object appears to respond not just to present conditions, but to accumulated history. If tidal interactions during the Earth flyby were sufficient to trigger this new phase, then similar interactions in the past may have left lasting imprints. Close passages near other planets, near its parent star, or even through dense interstellar environments could have progressively shaped its internal architecture. What we are observing now may be the final expression of a long evolutionary process, one that began long before this object ever entered our solar system. In that sense, 3I Atlas is not just passing through space, it is carrying a record of every significant gravitational interaction it has ever experienced. Perhaps the most unsettling aspect of this phase is that the object is leaving while still active. Most comets quiet down as they retreat, becoming observationally uninteresting long before they disappear from view. 3I Atlas is doing the opposite. Its most intriguing behavior is emerging late, after the closest encounter, after the moment when attention usually fades. This inversion of expectations means we are watching a system evolve in reverse, becoming more complex as it exits rather than simpler. In observational astronomy, that is a dangerous situation because it means the most important data may arrive when the object is already becoming too faint to study in detail. The clock is running, and every new pulse detected is a reminder that whatever changed did not end with the Earth flyby. At this distance from the Sun, the rules should be simple. Less energy and means less activity out. Thermal models are very clear on this point. As an object recedes, sublimation weakens, jets soften, variability smooths out. But 3I Atlas is refusing to cooperate with that logic. The pulse does not weaken in a clean exponential decay. Instead, it maintains a structured rhythm, suggesting that thermal input is no longer the primary driver. This implies that the system has become internally regulated, meaning the energy source controlling the activity is at least partially decoupled from direct solar heating. That does not require an exotic explanation, but it does require a rethinking of how energy can be stored and released inside small interstellar bodies. Another striking feature is endurance. The channels guiding material outward do not collapse as activity continues. In fragile cometary nuclei, sustained outgassing usually widens vents, erodes structure, and leads to progressive loss of definition. Here, the opposite appears to be happening. The jets remain narrow and repeatable over time, implying that the pathways confining the flow are mechanically robust. This suggests a material strength higher than expected, or a geometry that naturally reinforces itself under stress. Either way, it challenges the idea that this object is a loosely bound aggregate. Whatever its internal makeup, it behaves as if it possesses architectural integrity, even while undergoing dynamic internal changes. The regularity of the pulse hints at resonance. In physics, resonance occurs when a system naturally oscillates at a preferred frequency due to its structure and energy distribution. Once excited, that oscillation can persist with minimal external input. The Earth flyby may have provided the initial excitation, but the persistence suggests the object has an internal configuration that supports sustained oscillation. This is not something we typically associate with cometary bodies, which are usually damped systems that lose energy quickly. Resonant behavior implies compartments, boundaries, and feedback mechanisms, all hallmarks of structural complexity. Again, this does not point to intent, but it does point to organization. As these behaviors accumulate, a gap opens between what we observe and what we can comfortably explain. That gap is not a failure of science, it is the beginning of it. The continued monitoring, the extension of observation windows, and the reanalysis of earlier data all signal that the scientific community recognizes this tension. When an object forces multiple models to stretch at once, it becomes a priority case, not because it is mysterious in a sensational sense, but because it exposes blind spots. 3I Atlas is doing exactly that. It is not loudly announcing its nature. It is quietly insisting that our assumptions about interstellar objects may be incomplete. So this is where the story truly lands, not with certainty, but with tension. 3I Atlas passed Earth quietly, without spectacle, without danger, and without drawing attention from anyone who wasn't already watching closely. Yet after that moment, something changed. An object that should have been fading instead began to pulse. An object that should have been cooling instead showed structured, rhythmic activity. An object that should have behaved like a standard comet instead revealed internal complexity, chemical signatures, and directional precision that strain the limits of our current models. Nothing in the data requires an artificial explanation, and pretending otherwise would miss the point entirely. The real significance of 3I Atlas is not that it proves something extraordinary, but that it exposes how narrow our expectations have been. Our models are built almost exclusively on objects that formed here, in one solar system, under one set of conditions. This object did not form here. It arrived carrying a history shaped around another star, possibly over millions or billions of years, and it is now leaving before we can fully decode that history. What we are seeing after the Earth flyby is likely not a new phenomenon, but a delayed revelation. A system pushed past a threshold, settling into a mode of behavior that reveals its internal architecture rather than hiding it. pulses instead of decay, precision instead of chaos, activity that persists even as the object retreats into the cold. These are not violations of physics, but reminders that physics can play out in ways we have not yet cataloged when the initial conditions are unfamiliar. 3. I-Atlas is already on its way out. Its orbit guarantees there will be no second encounter, no easy follow-up years from now. Soon it will become too faint to study in detail, and eventually it will vanish completely into interstellar space. What will remain are the records, the light curves, the spectra, the timing of those pulses, and the uncomfortable questions they raise. Was this an extreme natural case? Almost certainly. Was it normal? Clearly not. And that distinction matters. Science advances not when everything fits, but when something refuses to. 3 I-Atlas has done exactly that. It has forced us to confront the limits of our assumptions, the gaps in our detection capabilities, and the reality that the galaxy is not a quiet place filled only with familiar debris. Interstellar objects are out there, passing through more often than we once believed, and some of them will not behave the way we expect. If you want to stay updated as new data comes in and as future interstellar visitors challenge our understanding even further, make sure you're subscribed. Because the next object like this may not announce itself clearly either, and by the time we realize what we're looking at, it may already be on its way out again.